Hey there, Allie's mom and Ben's mom. And there's another sibling that I met who I'm going to have in 105, and I've forgotten her name, and I apologize. But, hi. I was talking to Allie with math, which I love talking to Allie about math with, and she told me that she was talking to you, and apparently you kind of needed some more, like, convincing why a negative times a negative is a positive. And what is so awesome about that concern is it's not intuitive at all, actually. There's all kinds of ways to kind of explain it away. One of my Math 98 assignments actually is to have them journal on why a negative times a negative is a positive. And it's great because a lot of times they'll say something like, well, because two negatives make a positive. And it's, well, but that's not necessarily true. Like if you have -3 and then you subtract 3 more, you actually end up with -6. So two negatives don't make a positive when it comes to addition and subtraction. So why is a negative times a negative a positive? And I've stumbled upon one explanation that seems to help the most students, and I think it's because it satisfies their need for completeness in math. It's not a cutesy way of visualizing it on a number line or anything like that, but it actually satisfies kind of a neat need they have for, I don't need to memorize a bunch of exceptions, I need to know how it fits. So let me run it by you and see if it kind of makes sense. Because the trick with negative times a negative is a positive is that there's, since there's no positive multiple, you can't do the normal one. Like if you have, -3 times 2, you can't say, oh, that means -3 2 times. So that's -3 plus another -3 is a -6. So a negative times a positive is actually kind of straightforward. Like, oh yeah, I understand that. So here's what my students seem to like, and it ties into something called the distributive property, which is actually pretty handy. A lot of times it gets ruined in algebra classes by making you put a bunch of symbols in with it, but it's actually kind of a neat thing. For example, if you needed to multiply something like 101 times 99, something like that. Now you can do that with the algorithm all you want. 9 times 1, 9 times 0, 9. And you can do that all you want. Another way of thinking about it, though, is that 101 is 100 plus 1, and 99 is 100 minus 1. That's the same problem as that, because you can just rewrite the numbers as other numbers. And then you can use the distributive property. You take each of the numbers here and multiply it by each of the numbers there. So you do 100 times 100, which is 10,000. 1 times 100 is plus 100. 100 times -1 is minus 100. We can say -1 times 100. We're okay with that. And then plus 1 times -1 is minus 1. So it ends up that these folks cancel here, and then you have 10,000 minus 1, which is just 9,999, which is exactly the same thing you'd get if you did that up top. And the reason that that's kind of handy in general is you can mentally visualize. Like this requires an algorithm of carrying and putting ones up and stuff. This just requires you to keep 4 things in your head. And assuming you can free up enough drive space, sometimes I can't, but if you can free up enough space, you can actually, keep the 10,000 away. You can even just take a piece of paper and do it in your head, like 10,000, -100, 100, -1, and things like that. But what's cool about that way, let me find my eraser real quick, and I have no idea where I put it. Oh, this will work. Okay, so what's cool about it, though, is you can write it geometrically, and this is where I think students like it. If you envision kind of your workspace as this, and you're doing the problem 101 times 99, you can put the 101 as 100 plus 1, and the 99 as 100 minus 1. The size of these things is irrelevant. It's just breaking the whole thing up into 4 regions. And the 4 regions each correspond to those 4 numbers I had earlier. So this one times this one gives you your 10,000. That one times that one gives you your -100. That one times that one gives you a 100, and that one times that one gives you a -1. And then all you got to do is add them all together, and you get what you need to get. Hopefully that makes sense. Okay, so far so good, I hope. So we're going to do a different problem. A little bit of a different problem. Using the same idea, though. Same idea. I'm going to leave that there, actually. We're going to change it to 99. 99 times 99. Okay? Now, all that's going to change here, we're going to erase most of this stuff. I shouldn't say most of it, some of it can stay. That -1 is still -1, and that's going to become a -1. Now, we're going to do that old school first so we know what the answer is. Okay, here we go. 9 times 9, there with a 1. 9 times 9, 81, is an 89. 9 times 9 is 81, carry the 8 again. 9 times 9, okay, it's 81, or 89, excuse me. So you get a 1, get the 1, you carry this over, you get 18, you use 9,810. So we know that it's going to be 9,000, if I did that right, 9,891, 891, 1, carry the 1, 8 plus 9 is 17, yeah, 9,000, we know the answer's got to be that. Okay, now let's start doing the square math that's over here. Okay, so you got 100 times 100 is 10,000. Good so far. You also know that 100 times -1 is -100. You're okay with that. We're okay with that because of what we had written up there earlier. You also know that 100 times that -1 is -100. And then you get to this point where you're like, wait a minute, -1 times -1, I don't know what that's supposed to be. So I don't know what that is. Put a question mark there for a second. But I know if I did know what that was, I could add those four things together, and that's what that equals. So if I do, oh, that's 10,000. There should be a 0 there. Sorry, my bad. Entschuldigen Sie bitte. So that's 10,000. So if you do 10,000 plus -100 plus -100 plus the question mark, that has to equal 9,801. 9,801. So if you ignore the question mark, just leave it there for a second, but add the rest of them, you get 10,000 minus 100 minus 100, which is 9,800. So that implies that 9,800 plus the question mark is 9,801. That means the question mark has to be 1. Right? Because if this is 9,800 and that's 9,801, that means this has to be 1, which means that -1 times -1 has to be +1. And here's the way that my students buy it. And I'm not going to, you've watched enough to get the point. No matter what kind of problem you set up with this, it always necessitates, if you've got a negative there and a negative there, that one there has to be a positive to actually have the system of multiplication be complete. So if you need a more allegorical kind of explanation, I highly recommend Google it up. There's tons of explanations online. This is the one my students seem to like the best. It helps with the completeness. It gives you a way of viewing all the multiplication types of problems in this square methodology. I hope that made sense. Allie, we'll see you. No, we won't see you next week. I'll see your exam next week. I'll see you at 2:43. Say hi to Ben and say hi to your other sibling. And I'm wishing everybody well. Cheers.